Hi guys! So in the last video, we were looking at finding the general term of sequences, and we saw two examples in which we dealt with alternating sequences, arithmetic sequences, geometric sequences, and factorials, all in two examples. The thing that we didn't get to was dealing with powers like n squared and n cubed. So now we might look at geometric arithmetic or factorials still, but the focus of this is going to be to find the general term when we have powers involved. So we want to find the general term of the sequence we have here: -2 over 2, 1 over 24, 6 over 20, 13 over 40,320. Again, this is a fraction, so we're going to separate it into the numerator and denominator. Only the first term is negative, which means that probably this is not, or not probably, definitely this is not alternating. The negative was put with the numerator. This is where the probably goes, which means probably it was done on purpose, so we should leave that -2 in the numerator, have the negative there, not put it in the denominator. So we're going to start by looking at the numerator here. Our numerator is -2, 1, 6, 13, and so on. So remember that the first thing that we always want to check is this arithmetic or geometric? So to check if it is arithmetic, I'm going to do 1 minus -2 to get 3. So that means I'm adding 3. But if I do 1 plus 3, I definitely do not get 6. So I'm not just adding 3 every single time. So this is not arithmetic. So then we're going to ask, is it geometric? So I'm going to do 1 over -2. So I'm multiplying by -1/2. But again, 1 times -1/2 definitely does not equal 6. So nope, this is not geometric. Then we saw that a way to identify factorials, usually, is when the numbers get really, really big, really fast. So that is not happening here. We have -1, -2, 1, 6, 13. They're kind of like increasing at a pretty, I'll say, slow pace. They're definitely not getting giant really fast. So I am going to assume then that this is going to be some power. And what we already saw is that to get from -2 to 1, I'm just adding 3. Well, how much does it take to get from 1 to 6? From 1 to 6, I'm adding 5. From 6 to 13, I'm adding 7. So what I can see here is that the increase is increasing by 2 each time. So we said, I'm just going to note the things that we said. This is probably not a factorial, because not getting really big really fast. But then we said that the increase is increasing by 2. Well, it turns out that if the increase is increasing by 2, that means that this is going to be some manipulation of n squared. So a good plan for right now would be to write down the sequence n squared. Increase increasing by 2, some manipulation of n squared. So I'm just going to write down the sequence n squared. So what n squared looks like is 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16, 5 squared, which is 25, and so on. So then the question becomes, how do I get from n squared to the sequence in question? Well, what I can see is, how do I get from 16 to 13? I subtract 3. If I get from 9 to 6, I'm also subtracting 3. To get from 4 to 1, I'm subtracting 3. And to get from 1 to -2, I'm also subtracting 3. So what am I doing to the sequence n squared to get to my numerator? I'm just subtracting 3, which means that my general term for the denominator here is just n squared minus 3. Okay, so this brings us to our denominator, sorry. Our denominator, that's the wrong color. Our denominator was, let's just remember, I'm gonna have to go back up a little bit. 2, 24, 720, 40,320, and so on. So in this case, we can kind of easily tell that this is not geometric or arithmetic, but the numbers are getting really big really fast. So probably it's a factorial. But the numbers get big fast. So it is probably a factorial. Okay, so just to make it clear, how is it clearly not arithmetic or geometric? Well, I mean, 2 plus 22 gives me 24, but like clearly I'm not adding 22 again to get up to 720. And then 2 times 12 gives me 24, but 24 times 12 does not give me that 720. So, I mean, you can always go check if you're a little bit unsure, but the numbers are getting super big really fast, so that makes us think of factorials in any case. And when we think of factorials, a good way to start was the same way we started with n squared up there. Write down the sequence of factorials. So 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial is 120, 6 factorial is 720, and so on. And hey, indeed, the numbers that show up in my factorial sequence are some of the numbers that show up in the denominator. But notice I'm skipping a bunch of them. So what I'm going to do to figure out what that general term should be is I'm going to rewrite my denominator in terms of the factorials. That 2 was 2 factorial, 24 was 4 factorial, 720 was 6 factorial. Now 40,320, maybe you don't know that, so you could try what's 7 factorial, what's 8 factorial. You'll find out that it's 8 factorial. Or you can just kind of see that, hey, look, each time these are increasing by 2. So it seems likely that we will end up with an 8 factorial there, and we do. So 2, 4, 6, 8, we can see that that's 2n, but even if you don't see that, we can see that this is arithmetic. If we ignore the factorials, it's arithmetic. My first term is 2. The thing I'm adding each time is also 2. So this gives me 2 plus n minus 1 times 2 to get 2 plus 2n minus 2, which gives me just a 2n. That doesn't deal with the factorial part, so my a sub n for the denominator will be 2n factorial. We have the numerator now, we have the denominator, so my a sub n for the whole thing for my final answer is n squared minus 3 over 2n factorial. Final answer. We looked at the numerator and the denominator separately. All right, so we still haven't dealt with n cubed, so that will happen in the next problem. All right, so now we want to find the general term of this sequence. And again, the first thing I notice about this sequence, I guess not again, we haven't had alternating yet. The first thing I notice about this sequence is that it's alternating. So before I think about anything else, I'm just going to go deal with that alternating part. So I know it's going to be -1 to some power within. I want for when I plug in n equals 1, I want it to be negative. When I plug in 2, positive, 3, negative, 4, positive. So in other words, I want plugging in odd numbers to result in something negative. So in this case, the power of n works for that. Okay, so we've dealt with the alternating part. Now you'll notice that the first term is just 0, but we have the 5 on the bottom, and that's very kind of the person who created this problem, because that shows us how the denominator is advancing. So we're going to leave that 0 over 5. We're not going to simplify. And when we think about the numerator, we're just going to have 0. We're not dealing with the negatives. 0, 1, 8, 27, and so on. So first question is this arithmetic? Well, to get from 0 to 1, I'm adding 1, but I'm clearly not adding 1 to get from 1 to 8 or to get from 8 to 27. So not arithmetic. Our common difference of 1 does not work. Well, and it can't really be geometric because there's nothing I could multiply 0 by to get 1. Like if I were to do the ratio 1 over 0, that's like does not exist, infinity, negative infinity, something like that. So this is obviously not geometric as well. The numbers aren't really getting very big very fast. So let's see, what do I have to add to 0 to get 1? We said that's 1, 1 to get to 8, that's 7, 8 to get to 27, well, that's 19. So it's not that the increase is increasing by 2 either. So this doesn't seem like a factorial, and it doesn't seem like n squared either. That increase is not increasing by 2. So numbers don't get big fast. Maybe not factorial. And increase not increasing by 2. Maybe not n squared. So the next thing that we're going to look at is n cubed. And unfortunately, we don't really have like a great way of determining whether or not something is n cubed. So we're just going to write down what n cubed would look like. So n cubed is 1 cubed, which is 1, 2 cubed, which is 8, 3 cubed, which is 27, 4 cubed, which is 64, and so on. And hey, guess what? Those numbers are the same numbers from n cubed, except that I have this extra number beforehand. So we can think of this two ways. We've talked about shifts before. In this case, it turns out that I'm not starting at the first number, I'm actually shifting 1 to the left. Which means that this would be n minus 1 cubed. But another way to think about this, if that's a little bit confusing, if you're having trouble with the shifts, would be to write these numbers as cubics. So I could say that 0 cubed, 1 cubed, 2 cubed, 3 cubed. And notice that the 0, 1, 2, 3 is arithmetic, with an a equal to 0 and a d equal to 1. So when I plug that in, I get 0 plus n minus 1 times 1, which just gives me that n minus 1. We then add the cubed to it. So either way of thinking about it, as an arithmetic sequence that's then being cubed, or as something being shifted to the left, we still end up with that n minus 1 cubed. All right, now let's look at our denominator. So our denominator is 5, 8, 13, 20, and so on. So first question is this arithmetic? Is this arithmetic? So what am I adding to 5 to get to 8? That would be plus 3. So 5, in other words, we do 8 minus 5 to get 3. And then does 8 plus 3 equal to 13? No, it equals to 12. So it does not equal to 13. So that plus 3 doesn't work. This is not arithmetic. So then we ask, is it geometric? So 8 over 5, that's the ratio of the first two, which means I'm multiplying by 8 over 5. But does 8 times 8 over 5 equal to 13? It does not, which means that this is not geometric. Okay, so we've eliminated the possibility of arithmetic and geometric. Then, again, these numbers aren't really getting big fast. So that means it's probably not a factorial. If we eliminate everything else, we might have to like step back to that. But right now, they're not getting big fast. So we can just kind of say, let's think about something else, at least for the time being. Okay, so then let's just see. We said I'm adding 3 to get from 5 to 8. Well, I'm adding 5 to get from 8 to 13. I'm adding 7 to get from 13 to 20. Again, that difference is increasing by 2. So in other words, the increase is increasing by 2. Which means that this is probably some manipulation of n squared. So let's look at n squared real quick. N squared is equal to 1 squared 1, 2 squared 4, 3 squared 9, 4 squared 16, 5 squared 25, and so on. Well, what I notice is that none of these numbers are the numbers from up there. So how am I manipulating n squared? How am I getting from 1 to 5, from 4 to 8, from 9 to 13, from 16 to 20, and so on? Am I going to need to shift this thing, or is there some sort of common way to get from one term to the next? Well, it turns out I'm adding 4 to 1 to get 5, and 4 to 4 to get 8. Is 9 plus 4 13? Yes, it is. Is 16 plus 4 20? Yes, it is. So each time I'm just adding 4 to get from n squared to the sequence in question, which means that my a sub n for the denominator is n squared plus 4. Now my a sub n for the whole thing, we're dealing with the alternating part. We had -1 to the n for alternating. For the numerator, I got n minus 1 cubed. And for the denominator, I got n squared plus 4. And that is my final answer. A sub n is equal -1 to the n minus 1 cubed over n squared plus 4. All right, so now we've really dealt with all of the cases that we really see in this class. That's all. Bye, guys.